All right, hello and welcome back. My name is Cameron Kirk, and this is part 6 on how to complete assignment 2 for the MIT OpenCourseWare course 6.837 as taught in fall 2012. This is going to be the final part on how to complete assignment 2, so we're going to get it all done in this video. Specifically in this video, we are going to be finishing section 4, the skeletal subspace deformation. So basically what's going to be happening is as our skeleton moves, which we have drawn using OpenGL and spheres and boxes, as our skeleton moves and all the joints move, we want to take a mesh. First of all, we need to load in that mesh, and then we want to sort of average the points depending on its weight and its connection to the joints as they move. So if you haven't already, go ahead and read through this entire section. I am going to jump right into the code on this one. It's not too bad for this video, but there is a lot of different functions we have to fill out. So yeah, please read through that section, and when you're ready, let's go ahead and get started. So the first thing we are going to be modifying is in our hierarchy view, the Solution Explorer, over on mesh.cpp, we need to fill out these functions. Oh, let me make this like that. There we go. And then the font size should be good. So we're going to be doing this this load function, and what's going to happen here is we're going to populate, as it says here, bind vertices, current vertices, and faces, add your code here, and then load it up. Current vertices equal to bind vertices. So to do this, we are actually going to copy and paste our code from the load skeleton function that we made in a previous video. So I'm going to copy all of this code, basically everything inside the function, and we're going to bring it over here right underneath where it says add your code here. All right, next up, I'm going to delete the everything above the while loop. Just the if statement above the while loop. I'm going to delete that. Keep those variables there for now. So we have this if statement, and then, so that's saying if the file did open, we're going to create some variables and enter a while loop. All right, next up, we're going to delete the add joint section and the create joint and the attach this to parent. So basically all of these guys we're going to delete. And this leaves us with basically, a gutted out version of what we did in the load skeleton code. This is a good starting point. This speeds us along since we've already gone through this. We're going to move these variables. Except for the line variable, we're going to move these guys into the while loop. And we're going to get rid of this comment because we're not working with joints in this loop. We're working with something else. And then for the vector 3, we're just going to call this guy v. And we need to also, this is going to be our vertex for the bind pose. And then we're going to need a string. We'll call it s. And we are going to, because we're going to be working with the tokens, we're going to delete the index variable. We're not going to use that. And we are going to make a tuple 3f, tuple 3u, called f. Okie dokie. And then we are pretty much going to be doing this sort of code here. So we're going to grab a line and then we're going to read it in. But the way this input file works is we're going to actually, once we have our line loaded into the string stream, we're going to read that into S, and this token is going to hold what sort of data this line holds. So is it going to be a vertex or is it going to be a face? And it just so happens that that is going to be S. So if S is exactly equal to V for vertex, then what we're going to do is read in the next 3 tokens into V. So instead of core, we're going to do V. And then we're not working with index. We don't need that guy. Great. And then if the token is exactly equal to face, or F. Then before we do that part, we need to take our vertex here and push it back to the bind vertices. So the bind vertices is a member of our mesh, and we're going to do a dot push back. And we're going to push back a V, just like that. Same thing for F. If we have a face, we're going to take this face, and then in our faces, should be a faces, yep, we're going to push back F. And then we're going to change these V's to F's. Good. Good. And save it. And we're done. Let me double check that I did this right. Yeah, that looks good. Cool. Let's go ahead and hit play and see what we got so far to make sure everything's working all right. I meant to start this recording with what we have so far running, and I forgot to do that, but it's okay. Okay, so everything's still working. I'm pushing the S key, and what that's supposed to do is that's supposed to toggle our mesh between our skeletal model and our mesh model. And we can still manipulate the joints. Looks good. Oh, that's the foot. How about the knee? Looks good. Okay, close it down. Great. So moving right along here, now we're going to fill out the code for the draw mesh. So let's see here. If meshes don't have normals, we need to generate the normal per triangle. We're going to be doing that with the cross product. So one of the things about the cross product, and we saw this in the last video. Let's see if I can get a browser window open. Cross product, as we know from physics and from calculus and from engineering, I guess, the cross product is going to give you a vector that is perpendicular to your two vectors. So here we have A and B, and then C is going to be perpendicular to that. So that could be thought of as the normal. So here's another example. We're finding the normal here. Cool. So we're going to be using the cross product to do that. All right, we're not going to spend too much time here. Let's go ahead and get this done. So this code is actually going to look a lot like code we have written in assignment 0, which is our model viewer. Yeah, not much more to say. I'm just going to go ahead and bang out this code real quick. So we're going to do a GL begin, and we're going to do triangles. And if you're wondering, I am not doing this from memory. I am looking at our code from assignment 0 on my second screen here. I'm going to do a for I, and that's going to type out an entire for loop for me. I'm going to hit tab, and then we're going to do faces dot size. I push the down arrow to highlight size and then hit tab for autocomplete. And then I'm going to hit tab and come down here. And we are going to have, well, before we do this, it would be nice if we had some unsigned, oops, not union, my mistake, unsigned A, B, C. We need some variables to hold our index for our face. Yeah, because down here we're going to say A is equal to faces I 0, and then we do the -1. The only thing that's going to be different is in our code from assignment 0. They don't have this -1 here, but everywhere else they do have this -1, or we do. We did that in assignment 0. We're not going to do that here. I am deciding that I want to just do the subtraction here. It's a little bit less code to write. And yeah, I believe in the handout sheet for assignment 0, which I don't have pulled up right now, Actually, I'm going to pause the recording and pull up the assignment sheet from assignment 0. Okay, and I'm back. And yeah, so in assignment 0, they did this strange thing of using the index C minus 1. And what I'm doing is I am doing the subtraction here when they get assigned. So yeah, let's keep going here. Now that we have the vertices for the triangle loaded, we are going to calculate vectors to calculate the cross product. So we're going to make a vector 3f, and we'll call this vector A. I'm going to call it vec A. And this is going to be equal to the current vertices with index B minus the current vertices with index A. So this is basically final minus initial, and that's going to give you a vector, or the difference between these two is going to give you a vector. We're going to do a vec B, and we're going to do final position minus initial position, which is A. And let's see, I can probably quickly draw this out. I don't want to make this video too long. I really just want to get the code and get this thing done. But we'll take a quick detour. So here's what's going on. We have 3 points, and let's call this guy A, and this guy B, and this guy C. And what I've just done, or what we've just done, is we have taken B and subtracted A from it, and so that's going to give us this vector. And then we've taken C and subtracted A from it, and that's going to give us this vector. And then what we're going to see next is we're going to do a cross product, which will give us one of these two vectors, but it'll be perpendicular. Okay, cool. Let's close this. All right, so now I'm going to copy this, and this will be the normal vector. I'm going to call it norm, and this is going to be, I guess I didn't have to copy it. It's going to be from the vector3 class. We're going to use the cross function, and we're going to cross vec A crossed with vec B. And then we need to normalize that. And normalized means that we're taking its magnitude and keeping the direction the same, but setting the magnitude to 1. Cool, so now we're going to do this little number from assignment 0, which is drawing triangles. Yeah, so we're going to do a GL. I was considering pausing the video and typing it out and then letting you guys see it to keep the time down, but no, we'll just do this right here, right now. Comma. So I did a GL normal 3D, and then norm 0, comma, norm 0, comma, norm 0. We'll change this one to norm 1 because we're counting from 0, and this will be norm 2. And end that with a semicolon. Great. Now we'll do a GL vertex. And suddenly I've become paranoid that I'm not recording, so let me type this and switch over here. Make sure I'm recording. Okay, mic looks good, we're recording. Okay. Sorry, I've had that happen too many times now, where I lose footage. Okay, so we're going to take the current vertices at position A, position 0. So we're saying get this vertex, and then get the x value of this vertex, because we're working with x, y, z. We're working in 3D. Then we'll say comma, and then we're going to copy this and paste it, just like in assignment 0, which I do have a tutorial for if you have not seen it yet. Great. Now let's copy this whole line, and we will paste that 2 more times. Now this time, in Visual Studio Code, I can edit multiple things at the same time, but I don't think I can do that here. But anyways, in the second line, we're gonna change all the A's to B's, all the A's to B's, And then in the third line, we're going to change all the A's to C's. And this will draw our triangle. And then outside of the for loop, we can say GL end. There we go. And save that. Okay. Now let's hit the play button and hope that we get something pretty cool to look at. I will pause the recording so we don't have to wait. Very nice. So we are back and we still have our skeleton, but if you hit the S key, and I'm going to pull up the console here as well, you hit the S key and it switches to the mesh view. There it is. And I think that took a hit on my CPU performance. I think we're good. The only thing though is our modifiers do not affect the mesh, but they do affect the skeleton. So now we have to write the code that will allow us to manipulate the mesh. So let's shut this down and keep going. We still have more code to write, but this is looking good. So far, no mistakes. So scrolling down to the load attachments, this is where we're going to parse the attachment file, and then we are going to load the weights. Oh yeah, it says it right here. Each vertex gets a attachment weight, and this will tell us how much each vertex in the mesh should move proportional to the skeleton. So to do this one, let's copy our code. Right above this make a copy, we're going to copy the code we just wrote for the mesh load all the way up to IF stream. Input file stream, we'll copy that. We will paste it into here, the attachments. And then what we are going to do is we're going to keep our, keep this, and then we are going to create a vector of floats. So not a vector 3F, but a vector, which is a C++ standard library, collection, I guess. But anyways, it'll be of type float. Attach. We're going to name it attach, okay? And then the next thing we're going to do is we're going to make a float called value. And then we will keep our string stream there, and we'll get rid of these guys. Making sure my phone is on mute. We'll get rid of this guy. And we can delete these guys, and then we will say while SS. So while there is still something in SS, we are going to take the token out of SS and put it into value. And then we're going to take that value and push it back onto our attach vector value. And then we're going to take that attach vector and we are going to push it back. We're going to push it back onto the attachments. I feel a sneeze coming. Okay, it went away. We're good. There we go. Save that. And we are good. Yep, this is good. So this is saying we're going to get a buffer or a line. We're going to continue to read that line, fill up a vector, and then when that vector is full, we're going to push back that line onto the attachments, and then we're going to repeat the process while we can still get another line from the file. Cool. All right, so now we have completed this mesh.cpp. We can close assignment 0. We're done looking at that. Let's look at assignment 2. Where are we? Okay, we finished that. Oh, wait. File input bind. Yep, we finished that. Mesh rendering, yep. Attachment weights, yep. So now we are going to actually implement the skeletal subspace deformation. And This one is a little bit more involved than the last two, but we are going to try and get it done in this video. So we're going to start off by working on this compute bind world to joint transform. We're going to start off with this guy, and then we're going to do this guy. Now, this second guy, I know I definitely got it right. But this one ended up being very, very tricky to think through. I think if I were to do it correctly as the instructions describe it, I would have to draw it out and spend a lot of time, and I think there would be probably some bugs. It's pretty complicated. So what I ended up doing was actually sort of an exploit with the information that this paragraph is giving you. So here's what it's saying. We want to compute a transform matrix, and this transform matrix will translate us from the joint coordinate reference frame to the world reference frame. And then I might have said that backwards. And then for the joint to world, it'll give you a transform matrix that will go from the joint back to the world. So I found this one very straightforward, very easy to make. This one, I think I know what they're asking us to do, but it's just, for me, it was just too much work. So what I ended up doing was, since I know I got this one right, and then I know it says right here, the bind world to joint transform for any joint should be the inverse of the current joint to world transform. So it's saying this guy should be the inverse of what we get out of this guy. So what I ended up doing is I just used the exact same code for both of these guys. And then when I try to reference this matrix, I just take the inverse of it, and then it'll be correct. So yeah, let's go ahead and jump right in and knock this out. So we're going to be doing recursion again for these. We're going to go back over to our skeletal model.cpp, and we're going to go all the way to the bottom. And here is our compute world to joint transform. And yeah, so the problem with this is I believe what we need is we need to traverse all the way down to the joint, and then as we come up, push them onto the stack and save those transforms along the way. But I couldn't visualize this one in my head, so again, what we're going to be doing is we're going to implement this one correctly, and then we're just going to copy the code for this one, and then we're just going to take the inverse like the handout says, and then it'll work just fine with that. So yeah, so all right, let's jump right in. So the first thing we're going to do is we are going to clear the stack. We want to make sure we have an empty stack here. We don't want to deal with having the camera transform pushed on, so we're going to clear this guy. All right, and then next up we are going to push the root joint. So matrix stack dot push, and then we're going to push the root joint transform. Cool. And then we are going to set the root joint's bind transform. Arrow operator bind world to joint transform. We're going to set this guy equal to its transform. Okay. Then what we're going to do is we are going to loop through the children of the root joint, skipping the first one because the first one is itself. All right, so for the root joint dot children dot, oh yeah, arrow operator. That's smart. It knew what I meant. Okay, not arrow, sorry, not dot, but arrow operator children and then size. And then we're going to start at index 1. We're going to loop through and we are going to call our recursive helper function. And I'm going to call this underscore world to joint. And this will accept the root joints arrow operator children, the ith child, as the argument. So we're going to pass it that node. And then when we come out, we're going to matrix pop. Matrix stack.pop. Excellent. All right, let's go ahead and define our helper function. So this is going to return a value of void, and this will be a member function of skeletal model. And this is going to be recur. Let's copy and paste the text. There we go. Open close parentheses. It's going to accept a joint pointer. Call it node to stay consistent with my other code. Curly braces, and here we are. Now we're getting the red squiggly on this guy, and that is because I usually like to use the little wrench tool that shows up, but I guess it's not going to show up today. How about the light bulb? Create declaration. Good. Where did it put that? There it is. Okay. And did it put it in the right spot? Set joint transform. It did not. I want to cut this and paste it right underneath the compute bind world to transform. Save it. And save it. Cool. All right, so the first thing we're going to do when we enter into this node is we're going to push this node's transform onto the stack, and then we're going to set this node's bind transform matrix to the top of the stack. So we're going to push, and then this will be the node's transform, so arrow operator transform, semicolon, and then we are going to take the node arrow operator bind world to joint transform, set it equal to the matrix top of the stack. So matrix stack dot top. Okay. And okay. Now what we're going to do from here, of course, is iterate through all the children. So for I, and then for each of the nodes' children, we are going to call recur world to joint on this node's ith child, as we've seen before. And then when we come out of the for loop, we are going to pop our transform off of the stack. So we're going to pop the matrix one time. Pop. There we go. All right. And that is it. So we're going to repeat this same implementation. What's going on here? Oh, I need children.size, as we have done many times before. Okay, save that. And this looks good. So we're going to repeat the same implementation for the update current joint to world transform. So we're going to copy the body of this function and paste it into this function. And then we are going to change world to joint. We're going to change the name of that function to joint to world. And this hasn't been defined yet, but we'll go ahead and give it a definition up here. It's going to return a value of void. It's going to be a member function of skeletal model, and it's going to have that name, and it's going to accept a joint pointer named node. And there we go. And let's go ahead and make this definition. I'm going to click the light bulb create definition. It probably put it in the wrong spot. It did. So I'm going to cut that, paste it underneath this, save that. So I'm just keeping them together with the caller. Okay, and then save that. And then we're going to copy the contents of this recursive function and paste it into this function and save that. Cool. So let me just quickly talk about what I think needs to happen in order to compute this one recursively and not, I feel like I'm cheating the way that I'm getting the same answer and getting it to work. So I believe what we need to have happen is instead of, we can open up Paint. I'm just going to explain this very quickly in case if you're interested in spending the time on figuring this one out. So here's the parent node, and then we go to a child node. And what we're doing when we get to this child node is we are pushing. So let's see, this will be that represents a push. And then we're going to go to the next child, and then we're going to push that. So as we take a step down to a child, we're pushing. Now, what I think will be the correct implementation, but is very tricky to do it without any bugs, I think what you have to do is you have to traverse down to the bottom node, and then as you come back up, so as we're coming up, we're going to do a push. So right before we leave, we're going to push it on. But this poses a problem, and if you spend some time thinking about this, I think that's not going to work out. Other than that, I'm kind of confused by how to really get this one correct. But yeah. So anyways, I did it this way. Feel free to follow along with me if you're just interested in seeing this project work. What we're ready to do now is we're going to move on to deforming the mesh 4.4.2. So we're going to be doing this function here, updateMesh. And then after we implement this, we should be able to deform the mesh using skeletal deformation. So this is the final function we have to implement for the whole thing to be working, guys. So very excited to be getting this done. By the way, the extra credit after the core assignment is done, this is up to you guys. I'm not going to be going over how to implement any of these extra credits. Maybe in a future video, I might come back and revisit these, but at this time, I'm just going to do the core assignments. Okay. So let me double check that I'm still rolling. Okay, good. We're good. We're good. Okay, cool. All right, so here we are in updateMesh. The first thing we need to do is make a vector of vector 3s, vector 3 floats, of type vector 3 floats. And this is going to be called new vertices. You can name it whatever you like. I'm going to call it new vertices. And then we're going to iterate. So I'm going to say for I. We're going to loop through our mesh dot current vertices. Oops, hit tab without completing that. Dot size. So if the number of current vertices we have in our mesh, we're going to iterate through all of them. And in each instance of the loop, we're going to instantiate a new vector 4f, vector 4 float. And we'll call this one sum points. So the summation of points, this is going to be the accumulator. We're going to initialize this to 0. And then we're going to initialize vector 4f. Call this guy P, and this guy is going to be initialized using the mesh dot bind vertices index I, and then it gets the x value of this vertice, and then we're going to give it a comma, and we are going to, I think there's a better way to initialize. Let me pause the recording, something that's a little less typing. Okay, yep, my suspicions were correct. So instead of doing the copy-paste, if we look at the member functions for vector 4f, we can see that we can construct a vector 4f using a vector 3f and a float value. So let's try using that. I'm going to pass this guy a bind vertices, which is a vector 3f, and then we're going to give it a comma, and oh, it's even suggesting to us, and then we're going to say 1.0f. Save that. Did that work? No. How about we do .xyz? No. What type is bind vertices? It's a vector. Oh, so we just need to give it I. There we go. That makes sense to me, and it's happy with that. Cool, so that saves us a little bit of typing. Okay. Now we're going to iterate inside this loop. We're going to do another for I. This time we're going to be using j as our index variable, so we're not going to use I inside a for loop that uses I. So I type a j, and then I hit tab, and then now we're going to iterate through the joints. So all of the joints, joints dot size. There we go. So we're going to iterate through all of the joints, -1. And if the mesh dot attachments at position I, j is greater than 0. So what this if statement is doing is it's saying that if this attachment for this particular vertice and for this joint has a value greater than 0. So basically, if we have a attachment weight of 0, we want to skip it. We don't want to waste time doing the computation for this guy. If it has no weight, it's not going to it's not going to move at all based on the joint that just moved. We're going to say some points is plus equal to the mesh dot attachments. So we're going to take that weight of ij, and we're going to multiply it with the joint. So the mesh joints j plus 1. Now this plus 1 is coming from the fact that we need to skip the root joint, I believe, if I recall correctly. All right, we're going to do an arrow operator. We're going to get the current joint to world transform, and we're going to multiply this. I'm going to go to a new line. We're going to multiply this with the m joints plus 1, j plus 1, arrow operator, and then this is where my shortcut comes in, bind world to transform dot inverse, because we computed it to be exactly the same as joint to world, and the assignment tells us it needs to be the inverse of joint to world. And then finally, we're going to multiply it with the point. Okay, and then when we come out of this for loop, we're going to say new vertices dot pushback. The sum points dot xyz. Cool. And then outside of both for loops, we're going to say m mesh dot current vertices is now equal to the new vertices. End it there. Okay, save that. Let's press play and see what we came up with. I'm going to pause the recording while we wait for it. Oh, I actually got an error, and you probably did too. Yeah, there is no plus equal for vector 4f. There's no operator overload for that. So we're going to say some points plus. We're going to do it like that. Okay, save that, press play. Let's see what we come up with. Okay, looks like we compiled. Oh, I forgot to pause it. That's okay. We'll keep waiting. Almost there. All right, I got some windows that popped up. So we still have our skeleton, and we can still manipulate the joints. Oh. Oh. I'm having performance issues with my poor laptop. Oh, geez. Okay. Let me turn off. I'll turn off my camera. I think the audio is good. Yeah, I'm having really slow performance. Yeah, my CPU is getting pretty full. But we can still manipulate the joints. It's just very laggy. And then if I push S, is it loading? All right, let me pause the recording. Okay, I am back, and I was moving so quickly that I actually repeated a mistake that I was stuck on for a week in my first attempt trying to do this project. And so if you guys followed along with me, I kept saying copy paste. We're working with recursive functions, and we had a big accident happen. So, and this is totally my fault, and I did this mistake, yeah, my first time through on this project. And when I saw what was happening with our current results, I was like, hey, this looks familiar. I think I did the same thing I did when I first did this. So, yeah, so we're in the current joint to world, and we're calling recur joint to world. And when we go to recur joint to world, we're calling world to joint, which is wrong. Let's make sure we recurse into the function we think we're recursing into. So world to joint is called, and world to joint calls world to joint. And now joint to world is called, and it calls world to joint. So now that is correct recursion. So let's hit play again. I'm going to pause the recording so that we don't have to wait for this to load. Okay, so once again, I was going too quickly. The curse of the copy and pasting. We are setting the bind world to joint transform. We never set the current joint. Sorry, bind world to joint. Yeah, this is wrong because we are. So let me just back up here. We are in the update current joint to world transform, and we want it to be the other one. Hopefully that makes sense. So this function, current joint to world, we want current joint to world. Okay. And same thing up here. Okay. Let's save that and start it. Let me pause the recording. Okay, we are back, and third time is the charm. We finally have the skeletal subspace deformation. So yeah, if you've stuck with me this far, thank you so much. Please leave a like. This assignment 2 took so much time. Huge time investment for me to make these videos. And it actually took me a long time to finally get around to actually recording this. Yeah, I believe like just figuring out how to do the assignment took me about 60 hours. And that was just working like in my free time. And then getting to a point where I could actually make a video showing you how to do it, once again, took very many hours. Yeah, I'm so glad to finally be at this point where assignment 2 is done and working. I have started working on assignment 3, but I'm not going to make it a priority to put out a guide for assignment 3 unless if I see the demand for it. So if you could please give this a thumbs up. Let me know, hey, I'm waiting for assignment 3 in the comments section. And that will kind of help me kick it into gear and get assignment 3 out the door. In terms of other things that you could be on the lookout for, I got a few other tutorial series that I am working on, I'm very excited about, that is sort of getting away from the MIT OpenCourseWare series, but is still in the world of computers and computer science. So please get subscribed and keep on the lookout for that. Thank you so much for watching, and I'll see you guys next time. Take care. Bye-bye.